Is this on? Great. First of all, I'd like to thank the organizers, Michal and Simon, for putting on this really exciting workshop. And I've definitely learned a lot from all the coffee chats and all of the talks. So today it's my pleasure to tell you about a plan for an experiment. Regrettably, we do not yet have potassium silver polar molecules, but let me kind of try to motivate why I think going towards these highly polar species might be interesting, and then share with you some preliminary results from the experiment we're building at U Chicago. So for this audience, I definitely don't need to motivate why we would like to extend our quantum control toolkit from cold atoms to cold polar molecules. Let me just say that for applications in my lab, we're really interested in heavily polar molecules to leverage that tunable long-range interparticle interaction that's given to us by this electric dipole moment. And because potassium silver will be assembled from potassium and silver atoms, of course, I have to acknowledge the tremendous body of work that has come before us with all of the assembly of thus far only the bialkali molecules. This was, of course, pioneered by the Gilla group in 2008 and has by now been extended to many, many species, and has been such a fruitful method that to date has produced the only degenerate bulk gases of polar molecules, including in potassium rubidium, sodium potassium, sodium cesium, and we just heard sodium rubidium. So the field has been very exciting, and we think that more polar molecule species are yet to come. And if you will indulge me, let me share with you some of what I think are the great triumphs of our field. Many of you are sitting in the audience who actually created this work. And of course, we all know that in many ways, the creation of polar molecules in a single quantum ground state was already a groundbreaking accomplishment. But to extend that quantum control forward, we basically, as a field, take the path that was laid out to us from cold atom world, right? We demonstrate long coherence times. Simon's group has now even 15-second rotational coherence times, which is just breathtaking. Of course, people have now loaded molecules of many different species into optical lattices or tweezer arrays and start to study beautiful spin models. And we even see the beginnings of spin squeezing from Lawrence's group, really exciting. Controlled two-particle entanglement, and even the first I-swap gates from Harvard group of Kong-Kwen Ni. And who can forget the first degenerate Fermi and then Bose gases. And clearly, this bottleneck of quantum control is being finally overcome, probably in this latest generation of experiments. Here is a very, very heuristic cartoon where you can think of this vertical axis for bulk gases as going from very hot and low phase space densities to deeply degenerate. For arrays, you could think of this vertical axis as large entropy, high number of defects, high disorder, to low entropy, low disorder arrays in many groups around the world. And it's the shared goal of, I think, the entire community in this audience that we keep on pushing and breaking this bottleneck further and further. And in that way, on the quantum simulation front, that should give us access to these long sought after states of matter, such as the topological P-wave superfluid, or even quantum spin liquids in ordered arrays of dipolar molecules that have as of yet been out of reach. And I do not claim that there's only one path to circumvent this bottleneck, but maybe today let me share with you why I think ultrapolar molecules may offer three semi-independent ways to break through this bottleneck. Number one, we'll have arguably better evaporative cooling from the higher dipole moment. Number two, there could be some novel ways to generate low disorder, low entropy molecular tweezer arrays, leveraging what I'll call dipolar blockade. And number three, Sinyu already brought this up in his wonderful talk yesterday, just simply increasing the scale of the interaction energy compared to the kinetic energy will make certain critical temperatures far, far higher energy scale. And that could be another way to make interesting phases of matter appear that depend on the dipole-dipole interaction. So let me get into it, but first, let me introduce you the class of molecules that we're trying to tame at Chicago. So in many ways, this is deeply inspired by, as I mentioned before, the bialkalis. I do think that the reason that the assembled molecules mainly came from group 1 is because our community is very familiar and easy. Laser cooling group 1 alkalis is probably the bread and butter of many atomic physics groups. However, the bond that you create when you put two alkali metals together is not very ionic. It's a mixture of ionic and covalent. And like we remember from high school chemistry, the most polar molecules have the most ionic bonds. Think your textbook polar molecule is a salt, NaCl. You pair an alkali with something very electronegative that gives you a high permanent body frame electric dipole moment. And unfortunately, we cannot cool the group 7 elements. However, when I was kind of late into my postdoc, I read this highly influential paper, for me at least, from the group of Michal, and this kind of convinced me what I should probably focus my efforts on for the next 6 years. And the suggestion is if you take the noble metals, copper, silver, gold, they are laser coolable like the alkalis, but they are also highly electronegative for reasons of chemistry. I don't really understand it. But anyway, these dipole moments are now accessing the regime of order 10 dBi at most. So you're basically as polar as a diatomic molecule can get. To do better, you would have to go polyatomic, and I'm not crazy enough for that. So the dipolar interactions, to put an energy scale or interaction rate on it, could achieve megahertz scale for interparticle spacings that you can get with optical lattices and tweezers. I also have to acknowledge this is an effort that's shared by many groups around the world, and I hear even more from this conference. So my colleague at UChicago, Dave DeMille, is pursuing francium silver for a novel shift moment measurement, and I hear there are also efforts underway in Durham and here in Warsaw. So, okay, first part of kind of why ultrapolar, I think has already been very well motivated by speakers like Thijs and Sebastian. Basically, the thesis here is not controversial, I hope. The better evaporative cooling is achieved through collisional shielding, either microwave or electric field shielding. And this is expected to be more efficient when you have a higher dipole moment and a heavier molecule. So let me break it down. Even though we've heard many, many great talks about shielding, as a reminder, shielding has been achieved first for calcium fluoride in tweezers with microwave shielding, as well as in bulk gases of the bialkalis. As we've heard, this was critical to many species reaching quantum degeneracy, and here are the initial theory papers suggesting this trick. But basically, the higher dipole moment gives you a more repulsive barrier at long range, and this should shield against inelastic two-body collisions more effectively. The heavier masses, perhaps, is a little bit less intuitive to understand, but Thijs put it very well in his recent paper with co-authors. I think this is almost line for line from that paper. At a fixed temperature, when you have collisions between heavier particles, they are more massive and thus slower, and therefore the non-adiabatic transitions to undesired states are also suppressed. And so again, Thijs, Sebastian, and co-authors, I was very lucky that they actually calculated the expected two-body loss coefficients for potassium silver here on the bottom right and other alkali molecules. And here you can see that the heavy mass and the high dipole moment give you a rate coefficient as low as 10 to the minus 16 cubic centimeters per second. So translating that into a lifetime at a typical molecule density, the two-body lifetime simply wouldn't even factor into your molecule lifetime. You would be clearly one-body limited. And I would also mention that the double microwave shielding also could suppress three-body loss from removal of bound states, as we have heard. And the group of Jeremy Hudson has a very nice result where basically they showed that microwave shielding is universal for all polar molecules. However, experimentally, to achieve the Rabi couplings that are required for a degree of shielding, that minimum Rabi coupling scales as 1 over mass cubed times dipole moment to the 4th power. So here you can kind of quantitatively see why heavy mass, higher dipole moment help. And of course, this gives you easier constraints on experimentally designing the microwave and antenna. So to summarize this first section, potassium silver has an 8.5 Debye dipole moment and about 150 atomic mass units. So we expect that this technique will also be very fruitful for this molecule species. So the second thing, and this is kind of the first time I talk about it in public, eager to workshop ideas or hear some critical feedback, I think that there could be an alternate path towards generating low entropy arrays when you have an ultra high dipole moment. So let me break it down for you by first examining two kind of, I would say, leading sources of disorder in arrays of polar molecules. So currently, right, there are molecules loaded in optical lattices as well as tweezers. They all experience some form of disorder. If there are, for instance, defects in the array, then it's quite obvious why a 1 over r cubed interaction would be very disordered at the 100% level if you're, for instance, missing a molecule. However, both with laser-cooled molecules and assembled molecules in tweezers, this kind of top-level defect is being controlled, at least for arrays on order 5 to 10 molecules, and I expect a lot of progress will be pushed on that front in the coming years, hopefully getting to defect-free array sizes of maybe hundreds, maybe even more. A perhaps more pernicious type of disorder is what I would broadly term the disorder in the wave packet size, right? So these are not point dipoles, although everybody writes the equation as if they were. These are actually molecular wave packets. Now, undergrad quantum mechanics tells you that deep in a tweezer or deep in an optical lattice, there are different harmonic oscillator states. Only if you're at 0 temperature are you in kind of one well-defined harmonic oscillator state. But if you're thermal, then your wave packet spread, this is the root mean square error in a one-dimensional tweezer, not only has this like textbook h bar over 2m omega term, where m is your mass, omega is your trap frequency, but you pick up this annoying hyperbolic cotangent term. Basically, as your temperature increases relative to your trap frequency, the wave packet grows and grows and grows. Why should you care? Well, if you just stare at the dipole-dipole interaction, and if you have any disorder of your wave packet in the direction of your interparticle spacing, then it is obvious that you're going to pick up some disorder in your dipolar interaction, and that disorder will go as the disorder in your wave packet size divided by the distance of your wave separation. So again, this is a 1D calculation. Don't take it too seriously because molecules exist in 3D and real space. Actually, this is worse if you include disorder in all 3 dimensions, right? But how do you beat this disorder delta U over U? You can space your molecules further and further apart, but then you pick up the rather annoying disadvantage that your actual interaction rate will go down as 1 over r cubed. So one clearly wins if you have a more polar molecule. This is kind of a argument for something like potassium silver. Here the black dotted line is an arbitrarily chosen temperature of 10 microkelvin, and you should read that on the left axis, the fractional disorder. You can see that the fractional disorder at order 2 micron separation is well controlled, less than 10%, and simultaneously the actual fully polarized dipole-dipole interaction, which is this blue line, you read on the right-hand side for the absolute rate, it's still quite healthy at several kilohertz. So basically, to sum up this section, you want maybe colder, heavier molecules to push that dotted line downward. The solid line is the 0 temperature ideal limit. And you also want a higher dipole moment so the rate doesn't fall off a cliff as you separate further and further. So you might ask, okay, that's great, but what's the novel strategy? And again, this is something that I would be eager to have discussions with people. Right now, it's just an outline, a sketch of an outline. But let's say you have a thermal bulk gas, not even a degenerate bulk gas. As your reservoir, of course, you turn on microwave shielding and you actually dip in a few tweezers, right? So you could be in an interesting regime where if you have appropriate microwave shielding, that shielding in some limit can be thought of as a hard sphere. you have a hard repulsive barrier for potassium and silver. This barrier is pretty significant in size. 10,000 Bohr radius is about several hundred nanometers. It could be in a new regime where it actually exceeds the size of your tweezer waist, let alone the wave packet size of your ground state harmonic oscillator. In this regime, you could do something which some people call entropy engineering, and this is very inspired by how cold atomic fermions are loaded in the ground state of optical tweezers. Please see these references. So the idea is that you deterministically have a single molecule occupancy per site, and it is either very low temperature or in the ground state, ideally, of the tweezer. So this is what I term dipole blockade. As long as you have a large elastic rate, your tweezer-trapped molecules will be in thermal equilibrium with the bulk, right? Your T bulk can be order microkelvin. That's like 20 kilohertz. Now, as long as your trap frequencies heavily exceed that T bulk, you would be in the very favorable regime of being low temperature in your tweezer. And as long as your dipole blockade radius blocks out any double occupancy, you're in the nice regime where you don't have multipartite occupancy. So finally, perhaps maybe most obviously, is that when you increase interaction energies, maybe certain critical temperatures become within reach. Xin-Yu talked about this yesterday, really great motivation, so I'll just zip through the slide. But for fermionic polar molecules, wouldn't it be great if we could actually achieve the temperature for p-wave pairing? This critical temperature was calculated by Cooper and Shlapnikov. It's a fraction of the Fermi temperature, but how high of a fraction that is determined by your dipolar length scale. And of course, fermionic molecules have already achieved quantum degeneracy in groundbreaking experiments done at Gila and Munich. But for the more polar fermionic species, such as lithium rubidium with Xin-Yu, or perhaps potassium silver, one might ask the question, even if we achieve temperatures that have already been demonstrated, perhaps those would already be enough to see p-wave pairing. So transitioning now to specifics of potassium silver, we are very lucky to have the group of Michal be able to calculate all of these wonderful potential energy curves. I think there's a poster by Timon in the hallway. You can see that for details about the energy landscape. They even calculated singlet triplet mixing and Frank-Condon factors, which my group is very, very grateful for. So a few details, you have 8.5 Debye dipole moment. Unlike the bialkalis, this ground state is very, very deeply bound. It's very similar to ALF, actually. Basically, this enables shorter wavelength optical trapping, and with that, you can also space closer interparticle spacing that gives you, again, a host of possibilities. Silver and potassium both have a single s electron, so we expect that Feshbach resonances should exist. Of course, that's not a given. The ground state, the Stirop lasers are kind of experimentally feasible with well-understood fiber or diode lasers. Bosonic and fermionic isotopes are available, and the rotational transition is also quite convenient. So here's a picture of our lab in Chicago, and as a brief timeline, this experiment started almost 2 years ago, at which point we were building the apparatus and the vacuum system in a spare lab, a very dirty lab. We actually managed to trap potassium atoms and even optically trap them before turning our focus toward the harder element, silver. We took a break to move, 500 feet away to our brand new renovated lab. But since February of this year, we not only managed to subdoppler cool potassium, we got our first silver, what I'll term bright mott, and actually improved our atom number almost to 100 million atoms in May. And our next steps, which my students are hopefully implementing now, are subdoppler cooling of silver, followed by dual species trapping, and hopefully searching for Feshbach resonances later in the year. And this is just every experiment has to show you some silly cartoon of the apparatus. It's not as compact as Hyunyu's, unfortunately. We do have a silver Zeeman slower, which took some designing, and then we have a potassium 2D mott. Quite a standard quantum gas experiment. Silver is a little bit more unusual, so let me just show the level structure. I like to say it is more similar to hydrogen than the other alkalis. It has a single s electron in the ground state, a D1 and a D2 line, both in the UV wavelength. And it also has nuclear spin 1/2, interestingly. So we create it in a fusion cell, a commercial cell, heat it to about 950 C. We designed a decreasing field Zeeman slower to load the slow beam into the Mott coil. The Mott quadrupole, the B field profile is shown here as a function of different distance. The Mott quadrupole forms the tail end of the Zeeman slower, and we trap atoms right about here. So because this is a decreasing field slower for the experimentalists out there, we actually had to put a dark spot in our Zeeman slowing beam because our Zeeman slower operates quite close to resonance. You'll see that we are a big fan of dark spots in the lab. We actually have 3. And it was very exciting to get our first silver Mott a few months ago. First, let me acknowledge the incredible work done by the existing silver Mott groups. The first time silver was modded, I guess, was over 20 years ago by the group of Walter at MPQ. They managed UV technology. It was way worse back then than it is now, so I have, huge respect. And then also my colleague, Dave DeMille, has been exceedingly generous with information on how to cool and trap silver. They've had a silver Mott as of, I think, 2 years ago at this point. Anyway, in potassium silver experiment, we have a standard bright Mott. It is smaller in extent than you would be accustomed to with a typical alkali, and it's quite dense and has high scattering. So many of you know that high spontaneous emission rate can sometimes limit the densities of big Motts. You would like to go colder, denser, and from that you can actually block part of your repumping beam with literally a mask that we make from black nail polish, and we do this twice with 2 different repumpers, and we intersect the dark spots. Here you see a fluorescence image of our dark Mott. You actually see the shell of bright F=1 atoms around it, and the dark spot in the center is where our high density of silver lives. And this dark spot, from a very preliminary result, increases our number and therefore we think density by over a factor of 6. And on the right you see our typical lifetime curves of the silver Mott. And we learn about this dark spot trick from none other than Wolfgang Ketterle, who to my knowledge demonstrated this first with sodium atoms. Running out of time a little bit, so I'll skip maybe the details of potassium, just saying that the 2-dimensional magneto-optical trap, which is the source of our slow beam, was actually commercially obtained from Observatoire de Paris, and that sped us up a little. And we also implemented subdoppler cooling on potassium. So our results, where they are not exactly the state of the art, I believe the record still lies with the Paris group. We think that 90 million atoms at 6 microkelvin is certainly enough to achieve Bose-Einstein condensation of potassium using an all-optical evaporation method. And we choose the bosonic version of potassium just because it is much cheaper to buy this source than fermionic potassium. One big downside of this combination of species is that, to no one's surprise, the ultraviolet tends to ionize all of the alkali elements, so that's bad. You can here see the lifetime curve of our potassium Mott without the presence of UV, and with the presence of UV, the lifetime is very sad. So we will not be simultaneously loading these 2 species together, but this will force us to perhaps first load silver, trap it optically, and then load potassium. And then the next steps, I think, are very straightforward. A few interesting details of silver. The polarizability at the typical near-infrared wavelengths are very poor. So, could be factor of 10 worse than your typical alkali. That's very sad. So a brute force solution may be just to have a very high power optical trap beam, which we have already implemented and already traps potassium. The better longer term solution, which we're implementing now, is to do subdoppler cooling on the D1 transition. like the alkalis, this is expected to cool close to the recoil temperature of the atom. So with that, we hope we can quickly achieve Bose-Einstein condensation of silver and then pursue more molecule physics. And my final slide, just an overview. We're really excited to play with these highly polar species as kind of a new toolkit that could be unlocked with polar molecules. And with the high dipole moment, we think that perhaps exotic superfluidity or long-lived interesting quantum dynamics could be unlocked. Let me also mention that I'm building a completely separate experiment, kind of in the vein that we want to make how did Hans Christoph say, molecules are the new atoms? Well, for atoms, cavity quantum electrodynamics is a huge paradigm of the field. I probably don't even need to say this, but it gives us access to spin squeezing, to all interactions, quantum networking, right, among others. So I think if one were to combine the cavity QED platform with ultracold molecules, that would unlock all of those and more, including interesting opportunities to play with photochemistry or chemistry of quantum electrodynamics. And with that, come to the end. Let me first thank my students, particularly Michael has been the brave lead grad student on potassium silver. Angela recently joined. Nachiket is building the cavity lab, and we also have some very talented undergrads, especially Xiaoyu on potassium silver. I'd also like to thank our collaborators and friends down the hall, the group of Dave DeMille for sharing their expertise with silver, and for the group of Mariana Safranova who did the AC polarizability calculations of silver, as well as, of course, the person with whom it would be too scary to attempt potassium silver, Mahal Tanza and his group for the potential energy curves. I'd also like to thank the funding agencies and you for your attention.
Thank you, Zoe, for this wonderful talk. With these new kinds of molecules, how do you call them? Super dipolar, ultra dipolar molecules? That's nice. Questions from the audience? Yeah.
Are there anything known about the molecule-molecule collision? Could there be naturally be a barrier already?
Is there anything known about the molecule collision?
Yeah, because alkalis we need shielding because it's a barrier-less reaction.
Oh, it's too far back. I don't know if there's anything known besides assuming that they will collide much like the alkalis, and assuming that in many cases these polar molecule collisions in the long range look kind of universal, and so the same shielding techniques can be applied. Maybe some experts in the audience have more to say than I do, but I'm not aware of any.
Another question? Yeah. Hans Christoph.
Thanks for the very nice talk. What do you know so far about the Feshbach resonances? Is there any estimate about where they could be, or what the abundance is, and what the width could be?
That's a great question. This was, in my mind, the greatest risk of starting this project. 2 points. One practical point is that there's 3 isotopes of potassium and 2 of silver. So the choice of potassium was kind of risk mitigation, so that there are 6 possible isotopic combinations. Surely one may produce a Feshbach resonance below 1,000 Gauss, which is as far as our magnet will go. The second point is that, of course, without super detailed knowledge of the long-range potential of potassium and silver, it is very hard, just like the alkalis, to predict ab initio where they may be. Yet, Mahal and his students and postdocs, I believe, are calculating probabilistic models of potential, distributions of how many Feshbach resonances are per unit Gauss, given that perhaps the vibrational splitting of the ground X and ground triplet ground state can be estimated from the potential energy curves. So if you just kind of tune the energy of the least bound state until the next resonance appears, you can get a distribution of where the Feshbach resonances may lie. Please correct me if I'm wrong, Mahal.
Any other question? If not, I have one question. So you were speaking about microwave shielding or any other way of DC field shielding, for example, but because of the high dipole moment at the BI, you can use maybe the first shielding that was demonstrated at GILA in 2010 that just put them in optical lattice, 2D optical lattice. Because of the big dipole moment, you might just have them shielded right away like this.
Yeah, that's an excellent point. Sorry, I did not put the reference up there. Yeah, the pancake shielding
Yep.
where everything just polarizes. We did not choose to install DC electrodes in our chamber for a kind of technical reason. We actually had the whole electrode system designed, but then we were like, okay, how does it play with our magnetic dipole transitions or the microwave transitions? And we found that the presence of the electrode would actually severely hamper the Rabi couplings we could get, both to drive magnetic and electric. So long story short, that capability is not possible in this generation of the experiment, but it's good to keep in mind, and perhaps for other highly polar experiments, there are going to be, 4 now coming online and soon.
Okay, thank you, Zoe. And let's thank the speaker again.